Okay, we can start the second lecture of today, the second talk. Carlo Maccaferri will talk about classical cosmological constant of open closed string field theory.
Okay, so first of all, I would like to thank the organizers for organizing this conference, which is finally in person. It's very nice to see all of you here. And well, so I'm going to talk about this recent paper we wrote together with Jakub, and also some work in progress, but I think the work in progress will be mostly presented by Jakub in the talk after mine. And okay, so that's yeah. So let's start with the motivations. So the main motivation is that it is useful to understand string theory backgrounds as classical solutions of an underlying string field theory. And one of the reasons why this is useful is that that's like the usual paradigm of non-perturbative quantum field theory, that if you have an understanding of background as saddle points of your path integral, then you can understand at least in principle, how the non-perturbative contribution arises in scattering amplitudes, for example. And right, so from this perspective, we know quite well that the branes arise as classical solution of open string field theory, which is a sort of restricted theory where the closed string background is fixed and is not touched, and only the open string degrees of freedom can fluctuate. Well, now we know that this fluctuation can reorganize themselves non-perturbatively, and if you are defining your theory on a given D-brane now, thanks to these non-trivial non-perturbative rearrangements, then all the other D-branes that are consistent with a given closed string background can be explicitly realized as classical solution, at least in the bosonic string. But we also know something about superstring, of course. And right, so then there is one big guys that is not playing any role in open string field theory. It is the closed string background, right? So closed string background has also a lot of dynamical fields, and they can fluctuate. So a change in the closed string background in this perspective should be captured by a classical solution in closed string field theory. And then we are led to merge the two things, right? In general, we have D-brane in a given closed string background, and there are dynamical open string and dynamical closed strings. So it is natural that if we want to study D-branes in a fluctuating closed string background, then the theory we need should be open closed string field theory. It is a second quantized formulation where both open and closed strings can propagate. Okay, but right, so that's like the common thing, but then everyone knows and that open closed string field theory is like the most difficult. I mean, this is the most difficult, right? String field theory we have, because it's like it contains closed string field theory inside, which is already like a monster. And in addition to it, it has all the open string degrees of freedom. And in fact, it is hard, not just computationally, but also conceptually, right? It's not really clear whether there is a classical limit in which both open and closed string can propagate and things like this. Whereas in purely open or purely closed, it's completely well defined what is a classical limit. And so therefore, before embarking in this endeavor to really try to understand the brane dynamics in open closed string field theory, last year with Jakub, we thought that we should have tried to extract all the possible things out of this simple theory, which is just Witten open string field theory coupled to the so-called Elwood invariant, which is a linear coupling that couples essentially a non-shell closed strings to an off-shell open string. And then also we generalize this picture to the superstring, at least for Neve-Schwarz deformations. And right, so this was already a very good starting point, because just thanks to this very simple theory that you can treat completely classically, then we were able to understand precisely this picture. So you have an initial open closed background that is an underlying CFT knot with some given D-brane described by some boundary condition. Well, turning on this exactly marginal deformation at the same time essentially allowed us to describe how this D-brane deforms itself due to the change in the clustering background. Okay, so this is what I was talking. This was the subject of my talk at string field theory of last year, and it's developed in full details in these 3 papers. Okay, so let's see. Okay, so I don't want to review this thing, but let me just go, because I think it's important to motivate why we really need to do this thing. So this shift in the boundary conformal field theory that we described through this Elwood invariant, then it's important to understand how it is concretely captured in the theory, and it is captured essentially because this theory, this Witten theory with Elwood invariant, produces open closed amplitudes. Okay, and it produces them in, so here I wrote a few of them. And the nice thing is that essentially here the only propagating degrees of freedom is the open string. So you only have open string propagators. And this is a very peculiar decomposition of the modular space of Riemann surfaces with at least one boundary, where open closed amplitudes are essentially reproduced by sort of the minimal possible amount of Feynman diagrams that are consistent with a sort of second quantized description. So this is like a 2 bulk and 1 boundary. There is one single Feynman diagram that gives you this. Here there are 2 Feynman diagrams, etc., etc. So these blue lines are the open string propagators. And okay, so these amplitudes are just, so in a sense, they are just usual worksheet amplitudes. But there is an advantage of using the string field theory formulation, is that these amplitudes are naturally, let's say, regulated towards Riemann surface degeneration. So this, let's say, essentially the biggest perturbative advantage of using a string field theory description of amplitudes, because by this I mean that suppose that you are computing this amplitude here, that you have some bulk operator, and you are in a region of modular space where you develop this very thin neck. Well, you can ask what is the Feynman diagram that reproduces this amplitude in the open closed in the Witten theory, and then you will find, okay, so maybe there will be more Feynman diagrams because here, but you will clearly be able to associate this degenerating neck to an open string propagator. Okay, and this is essentially what allows you to treat all of these problems with infrared divergence in coming from open string propagation. Well, so these amplitudes that you get from the Witten theory with Elwood invariants, or the supersymmetric generalization, are all, let's say, regulated towards open string degeneration. And this is enough to give well-defined amplitudes for generic external clustering momenta. Okay, so if you allow your clustering momenta to be generic, then you can compute open closed amplitude, and you never have to worry about the possible emergence of IR divergences because of open string degeneration. And so in particular, this setting, I think it could be very useful to do this computation of the instanton contributions in clustering amplitudes. Instead of using a full-fledged open clustering field theory, one could just use Witten string field theory with Elwood invariant. I think that yes, the thing should work. But that's not what I'm going to talk about, because in these open closed amplitudes, there are other channels of degeneration, of course. There are clustering degenerations also. And so these clustering degeneration are usually not important when the clustering fields have generic momenta, because you can always analytically continue in momenta. But in general, in these background deformations, the deforming clusterings are sort of fixed at very low momenta, and most of the time they have actually 0 momentum. Okay, just think about graviton vertex operator at 0 momentum, which will deform the compactification radius of something like this. And so now this picture here, where you form this very long closed string tube, then you can ask how is this part of the generating modular space represented by a Feynman diagram of the Witten open string field theory. And essentially what happens is that this is this clustering degeneration that here is very clear, it arises in these Witten diagrams as very short open string propagators emerging, okay? And so this very short open string propagator essentially means that the clusterings are colliding, but unfortunately, so somehow the open string propagator knows how to regulate open string degenerations when the propagator is very long. And on the other hand, it's not, there is no first principle way of constructing a regulation of the towards clustering degeneration. So I think that the simplest example where you see this problem is just a bulk 2-point function on a disk. And then, of course, this has two degeneration channels. One is open string degeneration, where one of the punctures goes to the boundary, and this is so there is a single Feynman diagram that represents this amplitude. And so according to the length of the if the propagator is infinitely long, then this is open string degeneration. If the propagator is infinitely short, this is clustering degeneration. And unfortunately, this propagator is not telling you what you have to do. So if you write it in terms of a Schwinger integral, you see there is this epsilon here that is the natural regularization. It turns out to be a t to the epsilon here that regulates the region in t equals 0. That is precisely the very long strip. But there is no natural way to regulate the t going to one limit, okay? And so to do this, you have essentially, so the idea is that to do this, you have to understand this long tube as a clustering propagator, and then this would be natural. And that's precisely what open clustering field theory do for you, okay? So if you want to study clustering deformation, you have to deal with very soft clusterings, because these are the typically vertex operator that deforms the background. And therefore, you will have problem around clustering degeneration. And so if you want to do the things properly, you have to use open clustering theory. So that was somehow the conclusion that we arrived. So our aim, the aim of this talk and this research, is to understand the brain deformation from clusterings in the framework of a sort of classical truncation of bosonic open clustering field theory. And just to give you a picture, because I think everything I'm saying is essentially condensed in this picture. So that's the starting background. So I have a clustering background with a choice of clustering coupling constant and a given D-brane. Now to this background here, I will able to construct a clustering solution that will change my CFT to some CFT star and the string coupling constant to some GS star. And accompanied to this, so this just describes the change in the clustering background. And this is accompanied by an open string solution that describes how the D-branes adapt to this change of background. Okay, so that's somehow the things we are going to discuss. And so that's a disclaimer before I start getting questions about this. And so in this framework, D-branes are in probe approximations. Okay, so that's like ignoring the back reaction that the D-brane has on space-time. So that's what you usually do when you do perturbative string theory. And of course, I mean, I think this framework is rich enough also to trying to relax these in the future, but it goes beyond. And an almost equivalent question in CFT is essentially, so you have a BCFT that is described by a boundary state. You change the bulk CFT, then it's a natural question to ask how the boundary state changes under a bulk deformation. Okay, so this question was in part addressed by Fred Nagel and Gabriel in the past, and also by other people. Okay, so now it's time. So are there questions up to here? So that was my motivating slides. So the plan of the talk, so there will be some crash review of bosonic open clustering field theory. Then I will discuss how background shifts can be understood in this theory. Then, okay, so up to here it will be, let's say, completely formal. Then I will try to give some perturbative understanding of it. So I will consider perturbative background shifts in such a way that one can also do explicit computations. And so then there will be a final example where we will really take a change in the compactification moduli of some toroidal compactification in the bosonic string, just to see how the whole thing works. And then I will conclude. Okay. So bosonic open clustering field theory. So you first pick a starting clustering background, that is the CFT and a choice of string coupling constant. And in addition to it, you also pick a consistent D-brane that you can put in this background, that is a boundary conformal field theory. And then, okay, so then you will have, let's say, a clustering Hilbert space that are essentially the bulk operator of this boundary conformal field theory that as usual has to be taken to be level matched. And in this Hilbert space, there is a symplectic form that is essentially the BPZ inner product dressed with this C0 minus. Okay? This is the usual story of clustering field theory. And so the open string are just boundary operators on the other hand, and also they have their own symplectic form, which is the BPZ inner product on the disk, usual stuff. And there is also this grading that this degree that as usual is for the clustering. I think I take it to be worksheet Gauss number -2, and for the open string worksheet Gauss number -1. And so then with this ingredient one can construct a quantum BV master action for the open clustering field theory, which is naturally expanded in the genera and in boundaries. And each of these terms is as a peculiar power of the string coupling constant in front that is given by the topology of the worksheet. And this V, so these are essentially, so there's a picture for it. These are, I think you can think of them as off-shell amplitudes between with some boundary and some genera between K open clustering and so these are all the open string distributed in all the boundaries. So here you don't integrate over the full modular space, but you just integrate in the modular space with the Riemann surface degeneration removed, because these are the regions that will be covered by the propagators essentially. Okay. And so this is the consistency of the construction relies in the fact that this action should obey the quantum master equation. And now, since the action is a decomposition in topology, also the quantum master equation can be decomposed. Okay, so this is the BV anti-bracket that, of course, is defined in open and closed, and also the symplectic Laplacian is all closed. It has a closed string part and an open string part. And so this was the thing that I was saying, that just because of how this operation here corresponds to glue the surface in some ways. So if you glue through a clustering puncture, it means that you're doing this BV anti-bracket to surfaces. Then of course the two genera adds and the boundary adds. If you glue through an open string puncture to surfaces, the genera are just the sum, and the boundaries are B1 plus B2 minus 1, because essentially you lose one boundary. And the symplectic Laplacian means the clause means to do the twist sewing of two clustering on the same surface. So this, of course, increases the genus by 1. And so one just has to be a little bit careful of the topological interpretation of delta open, because in fact it makes a difference topologically whether you glue on. So if you have a given surface, it makes a difference whether you glue two open strings that are on the same boundary or on two different boundaries. And in fact, in the first case where the two open strings are on the same boundary, the genus remains the same and the boundary increases by 1. But if you have at least two boundaries, then you can glue two open strings from two different boundaries. And in this case, the number of boundaries decreases by 1, but the genus increases by 1, because you are creating a new handle by making this bridge between the two boundaries. Okay, so inside this big theory, then one can isolate, let's say, two complete classical sectors that are a bit trivial in some sense. So one is just taking the genus 0, boundary 0, so these are only clusterings, and this solves the classical master equation. This is just classical clustering field theory. And also one can set to 0 the clustering, and just consider the action with genus 0 and 1 boundary, and this is just classical open string field theory. Okay, so now the idea is that that's a quantum theory. Okay, so we would like to do some classical analysis of it. So we try to isolate classical sectors. Okay, so first of all, we can see that the genus 0 is a sort of isolated sort of classical sector, in the sense that if you just sum up all the actions for all the boundaries and keeping genus 0, then you can show that this solves this sort of strange quantum master equation where that is just quantum for the open strings, but it's not fully quantum. It's because here you are only doing this symplectic Laplacian that connects to open string on the same boundary. Okay, so that's kind of but anyway, so that's just a closed sector of the full BV master action. And now you can, so here the closed strings are, there is no closed string Laplacian. So here the closed strings are classical, let's say. So you can ask whether inside this sector here, you can also set the open strings to be classical. And well, this is well known that this is not possible. Okay, this is just a very fact in string theory. And the way you see it is that you further decompose this master action in boundaries. And okay, boundary 0, you just find the classical master action of closed string field theory. At boundary 1, you find this thing here that looks quite promising because here it has like a structure. But then you immediately see that this S01, that is essentially the open string field theory action, contaminates the boundary equal to master action. I mean, because essentially this is the fact that if you have two disks and you connect them through a closed string puncture, then you get an annulus. Okay. And so that's the usual story, right? That I mean, open strings at one loop and are the same as closed string at 3 level. Yes. But in fact, Barton and Zwieback understood a possible way out of this story is that you can still try to make some sort of classical string theory if you freeze the closed string degrees of freedom to be a classical solution of S00, of pure closed string field theory without open strings. And essentially, I think a quick way to understand this is that if you take this BV bracket here, and you set phi to be a phi classical, then here you find 0. So this thing disappears, and then you're left that this is 0. So then you have that this action here, where only psi is a dynamical variable, that is essentially S01, where phi is frozen to a classical solution, obeys the open string classical master equation. And okay, so Barton, of course, gave an interpretation to this. So this should describe open strings in a deformed closed string background that is given by this classical solution phi closed. Okay, of course, again ignoring the de Bruijnsweg reaction. And okay, so let me just try now to just convert this BV language in homotopy algebra language, because this is what will be useful for computations. So so now you can give a parameterization, an explicit realization of these actions. So that's like the closed string field theory action. You realize it with some symplectic form and some cyclic symmetric products LK. And now, if you ask these, then essentially you get, I think this is a small problem. And then you get that these LK should obey these relations that are well known to be the L infinity relations. And the same thing you can do for the S01. So S01 is composed essentially of two terms, and they are both important. So first of all, you can isolate terms where there are no open strings at all. So these are just, let's say, off-shell amplitudes of closed strings on the disk. And also, and then you have the pieces where you have at least one open string. So you can, so this is supposed to solve this BV equation. And they are asking for this implies this extra homotopy relation. So these are the homotopy relation of an A infinity algebra that essentially governs the pure open string field theory without any closed strings. And in addition to this, you have all these other things here. And in particular, it's important to notice that here you can set, so in this relation here, there is one relation in which this S is equal to 0 essentially. So that means that you don't have open string input and you have a pure closed string output. So these are homotopy relations that essentially govern govern essentially this part of the action, okay? And so here there is not, so there are no open string inputs here, there is a closed-string output. And in fact, this is some new homotopy relation that was not included in the Kajura-Stashev OCR, because in that theory, I mean, somehow they were only interested in seeing what was happening where you had at least one open string, because they were interested in like the open string dynamics. So we will see that these purely closed string vertices on the other end will be very important for the vacuum energy that we will discuss about this difference. So somehow, so that's it's important to keep track of this. Okay, so I think a better, I mean, also another way of understanding this homotopy relation. These I think are the condition in which a pure closed string amplitude with just on the disk will decouple BRST exact states up to terms of the boundary modular space. So to do this, you will need to use these relations. And okay, so I hope now more or less the algebraic structure is clear. And so the theory that we are going to consider is this S01, where the phi has been set to phi classical, and the psi is the open string field that can fluctuate. And this is precisely how we are going to write it. So first of all, that's kind of a conventional choice. We decided to put explicitly the worksheet, this partition function of the starting background as an initial vacuum energy. So that's, I think we are not obliged to do this. I think that that's kind of a natural choice that was also done by Barton. And I don't know, maybe you can justify this by saying that if you compute the tachyon-vacuum solution with this thing, then the action will be exactly 0. I think that's quite natural. So then there is this part here that is also a constant that is generated by this part of the open-closed theory that only contains closed string punctures on the disk. And so that's, as you see, is non-dynamical for the psi, but it is still there as a piece of vacuum energy. And finally, there are these open string products that can be obtained from the open-closed products in this way by essentially inserting k times the closed string classical solution in this MKL products. So these are the formed open string products. And okay, so the algebraic consistency of this action. So this action, I mean, we have already argued that it solves the classical BV master equation for open strings, and the homotopy. I mean, this is realized by the fact that these M tilde, they obey weak A-infinity relations. So weak A-infinity relation means essentially that you also have the 0 product in the relation. And this 0 product is really a tadpole, okay? So it's something, so if you look at here, when you have M0, this couples a single open string with to nothing, essentially. So it's like a, yes? But phi classical, this is classical. The club means classical, so that's frozen to a classical solution, yeah. So phi means close, so phi is already the letter for close, and CL stands for classical. Yeah, so this is already resummed. I mean, this is, so you're supposed to solve the closed string field theory equation of motion, and then with this solution will be extremely complicated. You are supposed to plug it into these disk vertices, and that will give some number. So we will see how it works. And okay, but the important point is to realize that this action here, as it is written like this, as a tadpole. Okay, so you are not in a good vacuum at the moment. Okay, so to have a good vacuum, you have to shift the tadpole. So you have to cancel the tadpole. And what does it mean to cancel the tadpole? It means to solve the equation of motion of the open string theory. That now they are no more homogeneous, but they have also a source there. That is this M0. So now you have to solve this thing here, and then you have to expand your initial theory by taking the open string field to be this vacuum shift solution plus the fluctuations, and then you will get this expanded action. Now the expanded action generates a new piece, a new vacuum energy that was not there before. That is essentially the on-shell on-shell value of the open string action, okay? And so this is the theory that you have to compute because that you have to consider because this theory has no more tadpole. So psi equals 0 in this theory is a good equilibrium point, is a Gaussian point. And so these are the two things that you see. They depend on the clustering classical solution and also on the vacuum shift classical solution. And so then you can sum them, of course, and we call them the total cosmological constant because that's what they are. They are a constant part in the action. And now it's interesting to understand whether this has some meaning, this constant part that is generated in the action. So the only way that we can ever does gauge transformation. So since this depends on an open string solution and a closed string solution, then we may wonder whether this should be invariant under gauge transformations of this solution. Well, the invariance under gauge transformation of open string is essentially trivial because this doesn't depend on open string and this is just the on-shell value of the action. So it's obviously gauge invariant under open string gauge transformations. What is much less trivial is whether this whole thing is invariant under gauge transformations of the closed string solution, L infinity gauge transformation of the closed string solution. Because, okay, that's what you would expect, right? So two closed string solutions that differ by a gauge transformation, they clearly should describe the same background. And this is a vacuum energy, so this vacuum energy cannot depend on the gauge orbit of the closed string solution. And well, so okay, so this I think in the paper we have a rather long proof that this is invariant, but I think now here we have a nicer proof that I think it's more illuminating. So first of all, you realize what is a gauge transformation of the closed string field theory solution. So it's formally this one, but this whole thing is realized as some L1 star. So that's just the kinetic operator of the around the new background. Okay, so that's like the shifted BRST charge on the new closed string background. And at the same time, you can variate this cosmological constant with respect to the phi classical. And if you do it, then you will see that you can here collect the variation of the closed string. And here you factor out a peculiar state that we call L star 0, 0. And this L star 0, 0 is this guy in particular here. Right, the nice thing is that this guy here, I mean, Jakub will talk more about this, but that's precisely the generalization of the boundary state in the new open closed string background. Okay, so this guy here is a closed string state, you see, because L are closed string outputs, so inside to this state, you have to feed the vacuum shift solution and the closed string solution, and you can show that this state is killed by the deformed BRST operator around the new closed string background. That's exactly what you would expect by a bounded state, right? To be killed by the bulk CFT, but now also the bulk changed, right? So you don't have the initial thing, and thanks to this, then it's immediate to see that this is so then this is L1 star phi close, L1 star lambda, the L1 you bring it there, and then you use the fact that this kills, so then you find that the cosmological constant is gauge invariant. And so the gauge invariance of the cosmological constant from this point of view is understood as a deformed BRST invariant of the deformed boundary state. I think Jakub will say more about this. And I think it's nice also to observe that perhaps here someone here in the audience, maybe Yuji, can recognize that this is just a generalization of the KOZ boundary state, where you also can change the closed string background now. Okay, so now let's go to try to give some okay, so there is a sort of conjecture at the basis of all this construction that is a sort of, let's say, it's trivial generalization of the background independence conjecture at the basis of open string field theory. And so the idea is that you start with this open closed background that is a CFT naught, GS naught, and some boundary state. Then in this open closed background, you have two solutions, a closed string solution and an open string solution, and this should bring you to another closed string background with another boundary state, okay? So the conjecture would be that the theory for fluctuations around this solution should be equivalent by theory definition to the open string field theory directly defined on this background, okay, with no dynamical clusterings. I hope this is clear. And so if you follow this line of reasoning, then you have to match the vacuum energies of the two theories, like the theories for the fluctuations and the theory directly built on the new open-closed background. And then you have to let, so the theory defined already here will have a natural vacuum energy that will be this, that is just the G function of the new boundary state times 1 over GS star, because in this background, the string coupling constant has this value. And on the other end, the vacuum energy of for the fluctuation, we just computed it before, is the initial this partition function plus this cosmological constant. So background independence, the assumption of background independent forces you to conjecture that this relation should be true. Oh, because that's what a clustering field theory solution does in general. Okay, so you don't know in principle. But you know, for example, that the simplest thing you could do, you could just construct a clustering solution that excites the Gauss dilaton to first order, and then non-linearize the solution, right, to continue. And then you know that the effect of this is like the dilaton theorem, is just to change the normalization of the action. We will see. It's more complicated than you may think. So even if you don't turn on the Gauss dilaton, it turns out that the coupling constant still changes to higher degrees. So it's a quite complicated story. But okay, I hope it will be clear. Yeah, so thanks, Martin, for this comment. So notice that between the two backgrounds, the coupling constant can change in general. So this is something that you have to take into account. And also, it's important that this is really a generalization of the good old Sen conjecture of open string field theory, in the sense that if you set phi classical equal to 0, then you have just pure open string field theory. And there you know that then your vacuum shift solution will just be a solution of open string field theory. You don't have a tadpole anymore. And then you know that for all classical solutions, this story should be true, right? That the on-shell action should be essentially given by the difference of the G functions. Okay, so that's like good that this just generalizes to a change in the clustering background. Okay, so now I finished, let's say, with the general panorama. So how much time do I have just to see whether I'm okay with time? Okay. I have 20 minutes, more or less. Okay, so I can take it easier. Okay, so so up to here, let's say we discussed, let's say, the story in a sort of completely formal way, assuming that we know this clustering field theory solution, assuming that we know this open string field theory solution. In general, this is going to be very difficult, right? Because these are non-polynomial equations. So if we want to have some sort of check on this conjecture, or so we would like to be able to do some computation to see how this mechanism works. So we start to consider perturbative background shifts. So now we don't consider, let's say, the most generic clustering field theory solution, but we just are less ambitious. We are just deforming our initial clustering background with the same sort of marginal deformation. And okay, so essentially we start a solution with an element of the clustering homology, and then we try to upgrade it to higher orders in the deformation in such a way that we solve this equation. Well, so that's the usual perturbative story. So you can set up a recursion scheme, and then, for example, you can try to solve these solutions in Siegel gauge for the clustering with 0 plus equal to 0. And so then you will find a second order correction that is essentially the propagator acting on the two string vertex, and a cubic correction, which is again a propagator acting on this other piece, and so on and so forth. And now, okay, so notice these things here, they are well defined as string fields as they are, because there is this B0 plus over L0 plus that is always multiplied by P0 bar. So P0 bar projects outside of the kernel of L0 plus, so you never have problems in applying this operator to any kind of the things. But the problem is that if in L2VV there is a component in ker of L0 plus, then this thing will not be a solution. It will just be a well-defined string field, and that's all. And in fact, this is captured by these obstructions. that, so if you want this thing to be a solution as it is, then you need these things to be satisfied also. So these are statements, so you see they have all P0 plus in front. So that means that these are statements in the kernel of L0 plus. So there are some states in the kernel of L0 plus that you're building that must be 0 if you want this thing to be a solution, okay? Okay, so this thing can be sort of taken as sufficient condition for exact bulk marginality in a sort of string field theory approach to bulk marginal deformations, say. And okay, so now, we have built this perturbative solution, and then we can build the clustering part of the cosmological constant that will have an expansion in mu, of course. So here I wrote it up to mu square. So at order mu, there is essentially the single clustering on the disk. So that's the 1-point function of V on the disk. And order mu square, there is this thing here and this thing here. So I think this is more illuminating. So that's the order mu contribution. It's just clustering against the boundary state. Mu square, it's a product of two clusterings, clustering propagator and boundary state. And in addition to it, there is also this part here that is just a disk with two clustering punctures that integrates, let's say, in the middle, in some region inside the moduli space, and that's all, okay? So remember, yeah, please. Wait, no, but that's a vanishing, okay, so a vanishing action in clustering field theory. But that's not, no, but wait a moment. This is not this is not a solution for the open closed theory. That's the point. Because you are not variating the disk vertices. So you're only variating the sphere vertices. So this, from the point of view of the open closed theory, this is not supposed to be a solution. This is not a stationary point. So yes, and it is indeed, it has zero energy. I mean, it has zero action for the clustering. These okay, so you're thinking somehow that there should be a sort of quantum dilaton theorem in the open clustering field theory, and there also. Yeah. Okay, so this is not so. Yeah. I guess that if one could have under control the whole theory, and so this would be really a theory, a solution of the open closed theory. So keeping into account the back reaction, then probably then this will still be yeah, sure. It is not. It is not. Yeah, but that's what I told you at the very beginning, right? That this is not a solution in the open closed theory. That's a solution only in the closed theory. Okay. Yeah. And so just remember that this thing here is the clustering part of the cosmological constant, so it is not gauge invariant. And I think there is a very physical way of understanding that this is not a complete object by itself, because you see that this is here, somehow you are sort of forming a string, a 2-point function on the disk. But this amplitude is clearly missing the region where you have open string degeneration, okay? So that's not a complete amplitude, therefore it's not an observable. And so to get this extra piece of the cosmological constant, then we need the open string vacuum shift solution, which looks like this, okay? So here you have your source, your tadpole, and then this is the kinetic term, and so on and so forth. So once you have the clustering solution, then you can search for your open string solution also perturbatively in psi, in mu. And again, you get, you get equation of motions. So you get this recursive structure, where you see that essentially all the psi's, all the open string states are at the end of the day seeded by the deforming clustering in one way or another. And so again, now you're supposed to solve this equation. But now, I mean, just look at this equation because perhaps they are a little bit less familiar than usual. So we had a long discussion of this kind of equation in our last year papers on open string field theory with Elwood invariant. But you can already see from here that this solution is very strange because so you're only going to be able to find psi1 if M10V is BRST exact as an open string state. And this may sound a little bit puzzling because V is an element of the clustering cohomology. So essentially, so in order to be able to do an open string vacuum shift, what should happen is that you have to take an element of the clustering cohomology, put it on the upper plane, and then you have to detect the state that is created by bulk boundary of E. And this state must be exact. So this state should not trigger on states in the open string cohomology. If it does so, this is an abstraction for the vacuum shift. Okay, so that's like the generalization of exact marginality to this case. Yes. Yeah. Yes, yes. So so that's a very yeah, which direction the D-branes will follow. I think that to this vacuum solution, to this tadpole solution, you can always somehow add exactly marginal deformations of your open string. I mean, I really didn't think about it, but I think that so that's the structure. So if you're sitting on in a good open string moduli space, and then you switch on you switch on the clustering deformation, then okay, so then it's not obvious that this moduli space will remain, first of all, okay? But some marginal direction may remain. This depends on the background, in fact, okay? So then if some marginal direction remains after the formation of the clustering background, then I would say that the construction of the open string vacuum shift is not unique because you can always move, let's say, you can always add to this solution here. Yeah, I think, yes, I think that, yeah, so I think that when you do this, okay, so that's my proposed solution, that is the natural solution, where I just do this. And so in principle, probably to this, I could also add an element, some open string cohomology, and this will correct the second order thing and so on and so forth. So this will be like this would be like the usual the usual open string marginal deformation.
Okay. Yeah. So it's kind of funny that there seems to be a third direction, though. That just.
Yeah, so definitely this solution here is unique to some degree, right? So, but yeah, I don't know. I mean, what is its characterization in the sense that you're saying? So if you still have like marginal directions after the clustering deformation, honestly, I don't know why you choose this one and not another one. I mean, I don't have yes.
Okay, thank you.
And okay, so the story for this vacuum shift solution, okay.
So I think this is exactly discussed by the paper 2006 by Fredenhagen and so on, right? So if you consider if you convert on self-Dell radius,
yes,
you have more choices for the conformal boundary conditions.
Yes.
If you change the radius of the compactification,
yeah,
then you in general, you cannot get more. So if you choose some more boundary condition, unique, which present in the self radius, then change the radius. You cannot get, you can only have a normal Dirichlet boundary condition. In that case, I think you have to solve the, not the marginal deformation for the open strings. It's more like a tachyon condensation, right?
Yes.
So
yes.
In that case, you cannot get this kind of.
Yes, in this case, this is exactly the point where the modular space is lifted by the clustering deformation, and therefore you're only left with a single marginal direction. That is just
no. But I still believe that it might be a consistent boundary condition for open strings, but it's not. It's kind of like a tachyon condensation.
Yes. So you will generate an effective potential that will have a minimum. And then you will be able to go through this minimum, but this won't be a marginal deformation. This is like a lump solution, or
So
this solution. No, this solution is So just think about, you have a D1 brane wrapped around some circle of some radius. Then you increase the radius of the circle, and then you're asking what is happening to this D1 brane. So that's I think is the picture that you have to have in mind.
Okay. Right. So this will trigger the tachyon condensation that Yuji's asking about.
Yeah. But indeed, I mean, with Jakub, we even computed this vacuum, these tachyon potentials, right? So so this is something that you can see actually just with the Witten theory. You don't need these all things. You can really see these Mexican head potentials arising. So these are like, I mean, things that before were marginal, and then after the clustering deformation becomes tachyon. And okay, so again, I mean, these are well-defined open string fields, but they are not guaranteed to be solutions. And if you want these guys to be solution as they are without any corrections, then you have to impose these extra condition that are essential. So these guys are just like also they have an effective field theory interpretation. These are essentially the asking that the massless tadpole of the open string is 0. Okay, so that there is no, there is nothing that sources massless open strings. Or if you want to understand them, these are saying that disk amplitudes with n deforming clusterings on the disk and a single massless open strings should be 0. Okay, so that's the condition for the existence of the solution. And okay, so then you have the solution, then you can build the open string part of the cosmological constant, which to start at second order in the deformation in this case. And that's the second order deformation plus mu square. And now in picture, this is precisely the thing that we're missing before. It's like the 2-point function with the open string propagator. And okay, so then you can put everything together, right? So when you put everything together, you see that the full cosmological constant, of course, it has an expansion in mu. And it's okay. So here you explicitly see the mu square contribution. That this looks like an amplitude. This is really an honest amplitude of 2 V's on the disk. But it's not difficult to do the exercise. Go to any order in n and see that essentially this gives you the n-point function on the disk of n deforming clusters. Okay. And so the way to convince even more that this is a correct amplitude, you just write it here, and then you ask how one of these V2 decouple. So if V1 is Q closed and V2 is Q exact, then you would expect this to vanish up to terms at the boundary of modular space. And indeed, this happens precisely thanks to the homotopy relation that is there at the basis of consistency of these vertices. Okay, so now I mean, things are becoming more and more concrete, so we can really do real computations. And so now we wanted to compute at least this second order correction to the full cosmological constant to check whether to see whether we can check or not our conjecture. And okay, so to do this, I just explain you what you do. If you're interested in details, I mean, you can ask me or you can look at the paper. So essentially, we realized that these open closed products with SL2C maps, local coordinates. And in fact, we found out that you can, at least for this simple amplitude, you can set to 0 the term in the middle of moduli space. And you just have, therefore, L2, which is like 2 clustering on the sphere. L00 is the boundary state. And then you have L01. So this has, let's say, an open string input and gives you a clustering output. And M10 is it has a clustering input and an open string output. Okay, so essentially we realize explicitly this homotopy relation by explicit choices of SL2C local coordinates. The second ingredient is that we choose a standard, let's say, deforming clustering of this form. That is like a natural matter deforming clustering, where this is a bulk 1-1 matter. And right, so then we were able to explicitly compute this to the very end, and that's what we got. So these two diagrams give rise to these two integrations. So you see so this is the disk with two clusterings, so it should be integrated from 0 to 1 essentially. So this is integrated from 1 over lambda O square. So this is like an open string stub parameter that you can regulate, I mean, as you want. And the important thing is that, so here you have an open string propagator that gives you this regularization towards open string degeneration. And here you have the clustering propagator that gives you this regularization here, y of s epsilon c, where y of s is this precise function of s. And this is, if you expand it in s equal to 1, this is 1 minus s times something. So this is a natural regularization towards 1, towards clustering degeneration. And it is the correct one, okay, because these things are very sensitive. So this comes from the ghost, and this is just the 2-point function on the disk, on the upper half plane of the matter operators. So this thing can be computed explicitly. And so you're supposed to do the computation at finite epsilon open and epsilon c. You get some analytic function of epsilon open and epsilon c, and then you send epsilon open and epsilon c to 0. And this essentially guarantees that all the tachyonic divergences goes away. And okay, so here I'm not commenting. So you could also have massless divergences, but you don't have them in this case. But they would be cured by this P0 bar operator. So this is a really well-defined object. And also from here, we understand what was happening in Witten theory. I think this is also interesting. So in Witten theory, we were obtaining only this term here, where lambda O was exactly equal to 1. So in Witten theory, we were covering all the moduli space, but we were missing the regularization towards clustering degeneration, okay? And so, I mean, I think somehow here it tells you that at least in these cases where you have a non-trivial contribution from clustering degeneration, Witten theory is really a singular limit of this open clustering field theory. And I mean, yeah, so last year, I mean, we were somehow arguing that we should regulate the divergence here exactly with this thing here, but the reasoning was exactly this, essentially. We were already using open clustering field theory to justify the regularization, okay? So, okay, so I think I'm approaching the end of my talk, so I think now I can give like a final example of an explicit computation of a very easy clustering background that you can have under control, see all the things, how they work. So we consider the formation of an Arine compactification. It means that, okay, we imagine our clustering background, that some D3 boson has been compactified on some D torus with the moduli that are let's say, summarized in a sort of here. So that's the graviton and that's the Kalbramon. These are constant things. And so this gives rise to an exactly solvable sigma model, of course, that you know everything about it. It's a free theory again. And inside this compactification, we also choose some boundary state that we like the boundary state there are also known. You can choose many of them. For example, I mean, the simplest of them would just be Dirichlet-Neumann directions, but in principle, if you have some, I mean, you could choose also other things, but let's say that we choose the Dirichlet or Neumann boundary state in this background. And we consider deforming this sigma model, the CFT given by the sigma model with a clustering vertex operator that is this. Let's say it's a generalized graviton. So this will be a part of proportion to the graviton and the Kalbramon. And okay, so this is clearly from the bulk perspective is an exactly marginal deformation. There is no way that you can make a 3-point function out of this. And also, for sure, for Dirichlet-Neumann boundary conditions, these are also unobstructed. So the D-branes are able to adapt to this bulk deformation triggered by this. And therefore, you can directly compute with the slide that I showed you before, you can directly compute this lambda of epsilon. And this lambda of epsilon has a term that is linear in epsilon that comes from the first order solution, and terms that are quadratic, and 3 terms that are quadratic in epsilon that comes from the second order solution, either the open string vacuum shift and the closed string solution. And okay, so so I just have to tell you what is epsilon tilde, because here we have epsilon. So here these are closed string amplitudes on the upper plane essentially. So the way the closed string enters is through this doubling trick, right, where you have to dress. So you have to dress the polarization with the fusion with this how they call it, this omega, these reflection matrices. Okay. And you know, these reflection matrices, they have some compatibility condition in order to preserve the energy momentum tensor at the boundary. And so this epsilon, so the cosmological constant naturally appears in function of the effective polarization, because it's computed on a disk. But okay, already notice one thing, that of course this cosmological constant is very sensitive to the gluing map omega, to the reflection matrices. Okay, that's what you expect, because it's some computation you're doing on some D-brane. But there is a term, this one here, that is independent of the gluing map. You see, because thanks to this property here, the gluing map that is hidden here, it just cancels. Okay, so that's an important thing that you have to keep in mind. So this term here is the same for every D-brane. This is what it means. Okay, right. So now we would like to compare this value of the cosmological constant. So our conjecture says that this cosmological constant should compute essentially the shift in the G function up to a possible change in the string coupling constant. And therefore, we have to have under control the shift in the G function from the worksheet perspective. Now, that's a completely solvable worksheet theory. It's a free theory, so you know what is the G function. What you don't know, though, is how a change in the Narain modulus E from the sigma model perspective is related to the polarization, to the strength of the deformation in the string field theory side. Okay, so these two things are not. I mean, they don't have to be the same, and they are not the same, in fact, in general. Okay, so that's the usual problem, right? That usually string field theory parameters and CFT parameters have a nonlinear relation. So if we want to say something about our conjecture, we have to solve this problem first. So this is a problem in closed string field theory. This has nothing to do about the boundary conditions. That's just the question of how a change in the compactification tori from the sigma model perspective, how is it related to the deformation parameter of the closed string field theory solution. Okay, I think in open string field theory we had this problem for a lot of time. Then I mean, it's kind of common problem in string field theory in general. And so the way we attacked this problem was through some result by Ashok Sen in this paper here, where he gave a very interesting way of building explicitly the cohomology around a marginal deformation in closed string field theory. So it gave a perturbative way to build order by order in epsilon cohomology elements in the deformed background. And therefore, if you are able to compare the mass spectrum around the solution, for the fluctuations around the solution, and the shift in the conformal weights in the sigma model perspective, so one will be expressed in terms of epsilon sigma, the sigma model, and the other in terms of epsilon, then these two things should match, and then you have the relation between epsilon sigma and epsilon. So we did this following Ashok's computation, and we found this, at least up to cubic order, we found that the sigma model parameter is the same as the string field theory parameter to first order, but then it has a non-trivial second order correction. And then it has a higher level corrections. So with this information, if you want, this information is sort of independent of this talk. So this could be like something by itself. I think going carefully through all these things would deserve like a new talk. Actually, it is actually quite involved how it works, and also not completely clear. I mean whether here you can maybe get some dependence on the string field theory data or not. I think these are things that are a little bit obscure at the moment, but for sure you can do the computation, let's say, for large closed string stub and find this thing like this is well established. And well, so yeah. So Ashok did. So Ashok was able to show that so the upshot is that according to the computation of Ashok, this thing is independent of the local coordinates of the closed string local coordinates if you do the computation for large closed string stubs. Okay, so you do large closed string stub, then you can still do some change in the local coordinates after the stubs, and these changes are essentially not giving any contribution. I think what we did not. Yeah. So we don't know. In fact, I think we have some arguments to believe that this should not depend on the length of the closed string stub. So a possible dependence on at least for this particular deformation. So this particular deformation is very peculiar. Okay, so it is not what is going to happen everywhere. But for this particular Delex, so it is possible that this won't depend on the stub, on the length. But if Ashok is online, maybe he can comment more on this. This is his computation.
Yeah, I think I mean it came out this way, but I didn't have any deeper understanding of why it's independent of the stub length. I mean, it just came out at the end of the calculation.
Yeah. And okay, so let's say at least for this very simple element, so we can think that this is like what it is, and then we can essentially so we had the cosmological constant written here. We can rewrite it in terms of the sigma model parameters. And then what we are able to find explicitly is this relation, which is true up to, so here I wrote it as an exact statement. Of course, it's true up to cubic order because that's the order where we are able to go. So this is nice. So you see that this is the G function. This is the initial G function. That's the deformation given by the open-closed cosmological constant. And that's the G function of the deformed Narain lattice, where the deformation is epsilon sigma of epsilon. So the deformation is still controlled by the string field theory parameter. But then there is also change here in the prefactor. And in fact, we find this thing here. So we find that the string coupling constant receives an epsilon square contribution. Okay. And you see that this contribution here is really of the kind that I showed you before. This contribution here is independent of the boundary conditions. So that's really a universal contribution that is independent of all the possible D-branes that you can put in this Narain compactification. So that's we took it as a sort of consistency check that this can really be understood as a change in the string coupling constant, second order. Okay. Yeah.
It is quadratic in epsilon. So it looks like as it were originated by something like the Nambu-Goto action. Well, Born-Infeld, but Born-Infeld is for the for
No, so that's exactly what doesn't match in the Born-Infeld. So okay,
Born-Infeld would depend from, but this is why I was saying Dambugoto. Dambugoto, it has something which goes like
yeah. So
because you write Dambugoto with dilaton.
Yes.
Okay.
I think that this is like I mean, to me, I mean, this is just what we found, and but I would really like to understand this effect better. I mean,
so is it not the standard Born-Infeld?
So it is the standard Born-Infeld once you factor out this part. So this is the standard Born-Infeld for the Dirichlet boundary condition. That is like like say square root of G plus B, square root of E. But then you have in front this E to the minus 5. Right? That is this guy here. Yes. Yeah, we should be the dilator somehow. Yeah. So, yes, yeah. So the fact is that the phi in the Dirac-Born-Infeld comes from the sigma model, where the phi is the coefficient in front of the R2. But here on the other end comes from the closed string field theory solution. So there should be some mix in the between let's say. So in general, you could try to. I think that so that's something that. We would like also to understand. So here we did not excite the solution with the Gauss dilaton. Okay, so we really choose to use just this pure matter vertex operator. So it's not inconceivable that you can correct your solution and give to it some sort of Gauss dilaton in such a way that the shift in the coupling constant given by the Gauss dilaton offset the shift in the coupling constant that comes from here.
It reminds me the old story of Seiberg-Witten. When you turn on the B field, you get the effective change in the coupling constant as well.
Yeah. Yeah, for sure. This is not. So this is not just square root of G plus B. I mean, so that's like a factor out effect, a factorized out effect. No, because there is this epsilon transpose. It is because of this. In G plus B, you would not be epsilon transpose. You would just have epsilon. That's the thing. Yeah, so this was a long puzzle we had with Jakub. I mean, we were trying to get this from square root of G plus B, but we were not able to do it. I mean, I think it's just impossible.
Yes,
this
is it's
just in the other way. So this has to be identified with something else to do with the dilaton. But yeah, so I think we are able to fix it indirectly by asking that this relation should be true. And okay, so I think I can conclude. And so, okay, the nice thing is that with respect to what I was thinking last year, maybe 2 years ago, is that at the end of the day, it doesn't seem that this three-level open clustering field theory is so difficult. For sure, the kind of computations are the same level of difficulties that we encountered in Witten theory. Actually, the use of these SL2C vertices makes things even more fast than what they are in Witten theory, where you have these Witten vertices that you have to massage a bit before being able to get amplitudes on the upper half plane. And okay, it is conceptually clean, and it allows to treat open and closed string degeneration in a sort of consistent way. Okay, so it's also you see that the string coupling constant participates non-trivially to the background change, even if the Gauss dilaton is not switched on. Okay, so I was somehow having this thing in mind that to change the string coupling constant in closed string field theory, you have to turn on the Gauss dilaton. So I think it's something at least curious, the fact that this solution to second order in the closed string deformation changes the string coupling constant without turning on the Gauss dilaton. So it's curious at least. And okay, so I think that one could argue whether in this space of observables that one build in string field theory, one can cook up an observable that measures the string coupling constant. So this could be also like an indirect way of seeing whether a solution is changing or not the string coupling constant. Okay, so here, thanks to this cosmological constant, we have something that depends on the ratio between the G function and the coupling constant. So we just have under control this ratio. So if we could have like an independent observable that can just measure, or maybe some other combination of G function and coupling constant, then we could really so you see, isolate the G function and the coupling constant. So at the moment, we can just measure, let's say, the ratio of these things. And yeah, so exactly, I think related to this is about what is the role of the Gauss dilaton. Okay, one of the things that we are trying to do with Jakub is essentially to repeat this analysis for a perturbative solution that is just purely Gauss dilaton. Okay, so that is essentially, I mean, you start with a Gauss dilaton and you build a marginal, a sort of marginal deformation with the Gauss dilaton, and see what this cosmological constant comes out. Okay, so this should be, so in that case, I think we would expect that we should not be able to change the bulk CFT. We should just be able, so this deformation should just change the string coupling constant and that's all. But I mean, we have to compute it, right? It's something to be done. And okay, so let me tell you that most of this story generalizes very nicely in a sort of non-trivial way to the superstring, at least for NS deformations. And Jakub will spend, I think, a good part of his talk explaining the progress we made in this direction. And yeah, well, as I was also saying, I think this formalism is rich enough. You just try to look at the other terms in the open-close action. So it would be nice also to characterize how a D-brane changes the closed string background by back reaction somehow. I mean, this should be related to the effect of the open string loops somehow. And yes, okay, so thanks if you have comments. And yeah, thank you.
Are there any questions? So I about this dilaton. So you're not actually looking at the dilaton theorem in this context. You just want to see the somehow just the shift in the vacuum energy.
Yeah.
So have you thought about whether whether there's like a ghost?
So the dilaton theorem is essentially expanding the action around the first order solution of
yes,
the
but then you have to have the field redefinition, which I was wondering if you and Jakub had thought about that in this context, seeing whether you could change the coupling constant in front of Witten's action or something. Okay, so in the case of the Witten action with the Elwood invariant, it's not clear exactly. The Elwood invariant doesn't seem to have a ghost dilaton. So.
Yeah. So this was also a limitation that I didn't mention with the. So the Witten theory with Elwood invariant, let's say, works well at modulo these problems at closed string degenerations for for closed string deformations of this kind CC bar V. There are 0,0 primaries. But the ghost dilaton is not a 0,0 primary, and you try to put it at the midpoint, it just doesn't work.
Right. So, but you could, in principle, now study this question in the context of the open-close.
Yes.
Your classical open-close.
Yes.
Theory.
So that's exactly what we would like.
I guess the expectation would be that that you can find some redefinition of the closed and open string field that would somehow
that would just
generate this a change in this coupling constant.
Yeah. So at the moment, let's say that maybe I can tell you something. Okay, so we can of course write down formally, right, the Gauss dilaton solutions. These are just propagator acting on vertices, and in fact we have a nice computation that, I mean, perhaps it is obviously expected since these are one parameter family of solution that should have zero action. But we have an exact computation of the action of the Gauss dilaton in closed string field theory, and we can show that it vanishes really order by order. And so just to get in practice, right? So, but now we would like to generalize this kind of computation in the open string side of the story. Yeah. So yeah. So yeah. So
and then you don't expect the action to vanish in that case, right?
No. For the open string, it should not vanish.
It should just be Okay.
Yeah. So I mean, according to our conjecture, it should just be the same G function over a new coupling, over a new coupling constant. That
so
is
it's
related
the difference in the inverse coupling constants.
Yeah, yeah. I think that from there, in principle, we could relate the VEV of the dilaton to the change in the spread, the VEV of the Gauss dilaton to the change in the string coupling constant order by order in the dilaton deformation.
Okay. Yeah. Thank you. Are there any other questions?
So there are closed string field theory solutions which change the value of the closed string coupling, right? I mean, you turn on the closed dilaton. Then there are solutions when you turn on some relevant operator, right? That you claim they also change the string coupling constant. That's why it was a big deal in this talk. But then maybe there is some other solution which turn on the relevant solution, but brings the coupling constant to whatever value you wish, in particular the previous one. So it in effect, it doesn't change it.
Yeah.
So maybe that's a better starting point. It's like a simpler situation that you can investigate, and so you would have but less troubles.
Would you know? I mean, what would be a closed string field theory solution that doesn't change the string coupling constant? I mean,
yeah. So you have to know how to measure it, how to like what is the invariant that tells you what the coupling constant is, and so this is not.
This is not known to me. I mean, it would be very nice to have some gauge invariant object.
Well, you could turn on your marginal operator at order lambda, and at the same time the Gauss dilaton. Lambda squared. And then this way you could somehow.
So you will correct order by order, and you know that you're not changing. But this is something that you have to do.
That's a little bit more complicated.
But it would be nice to have a direction that you know that if you take this direction, let's say it's a sort of linear combination of marginal operator plus Gauss dilaton, that perhaps is also depends on the string field theory data to some degree. It will depend probably. I don't know, but we don't know. So I think Jakub wants to make a comment.
Yeah, just to recommend to what Martin was saying, that it would be nice to have an independent observable which measures just the coupling constant. So you are thinking, Carlo, that this could be provided by the on-shell 3-point amplitude for closed strings around the shifted background. But then again, there's this dependence on the external on-shell states which you put into the amplitude. So I wouldn't say it's like a very elegant way of measuring GS, but certainly one would be able to infer some information or GS in that way.
In order to have a physical meaning, to compare to something you can measure, you have to suppose that you are more or less asymptotically Minkowskian in order to define an S matrix, first of all. And the 3 points are always on shell 0, but for massless fields which are collinear. So it is not strictly physically, it's somewhat a kind of mess.
I mean, if you just consider 3-point amplitude for tachyons, which conserve momentum, of course, that is non-zero, right? It's just basically proportional to GS.
Well, you can also probably use graviton at complex coupling, right? Complex momentum. That's also probably non-zero.
Yes, but it is not a physical measure.
Well, complex on shell. I mean, you can take complex on shell. So we are still invariant.
Yes, complex on shell, but the 3-point, 3 graviton complex on shell are only kinematically different from 0 when they are collinear.
Because of momentum.
Is that right?
Momentum conservation.
No, but if you go to
the 4 point, okay, but you need a lever, anyhow, a symptotically flat space to define it.
Now, you see, I think the problem is that independently of the vertex operator you use to compute this 3-point function, is that this is going to be effectively be at least a 5-point function, because it will be a 3-point function deformed by the solution That is, I mean, if you want to detect this change in the string coupling constant, you have to go at second order in the solution. So you'll have to compute an amplitude with 3, let's say, on-shell states, and 2 deforming closed strings from the solution. So this will be a closed string field theory, a 5-point closed string field theory amplitude. And I think it's probably difficult unless there is some miracle, maybe, you know.
So in open closed string field theory, so Ternino Dilaton expectation value also changes the open string coupling constant.
Yes, so that's what our computation suggests, right? Because our computation is really detecting a change in the normalization of the open string field theory action, essentially.
So I see. So
yes,
there must be a precise relation between the closed string coupling and the open string coupling.
So what we are here, I mean, honestly, we are really measuring a change in the open string coupling constant, but yeah.
Thank you.
Maybe give the.
So this no open string inputs and closing.
Yes.
Indeed, was not in this Kachura.
No.
But it was in the quantum algebra. There it appeared already.
Oh, I see. Okay,
So
because
otherwise
this was something that I wanted to ask you, because looking at your paper, I was not able to find these vertices, but maybe they are hidden in.
You need it there, otherwise the delta operation doesn't work
properly. That is of course what one would expect, but yeah, perhaps you can show me then the detail. Would be very nice. Thank you.
But you were just saying that those vertices are in the full quantum open-closed homotopy algebra.
No.
Yes, but okay, that was that was known, I guess. But Carlo has some kind of generalization of the open-closed homotopy algebra, somehow the classical open-closed homotopy algebra.
Yeah.
So
it's classical but non-dynamic.
Has that been known before, that the generalization that Carlo is discussing, this sphere disk homotopy algebra?
Yes.
Okay. Any more questions? Okay. Let's thank the speaker again.